I'm going to record so that I can post it in case people didn't get on and wanted to listen. Okay, so welcome to everybody. I was just saying a little bit about the schedule. We got a note from the chancellor, said that we're going to be online the rest of the way. And so my plan is for you guys to keep working. Our class was already on my stat lab, so you got all the homework. It was all online anyway. What we're going to have to figure out, hey, Jacob, welcome back. It's looking good. I like how you moved outside. Our plan is for you guys to keep moving forward on the homework. I will continue to post it, try to stay a week or so ahead of you. It's been hard this week because I'm trying to set up all this online stuff. But I will get back out in front of you. There'll be homework on there, so you just work it out. The hard part is going to be that as we move to online, it's going to feel a little bit more like an independent study type class, right? Where you're going to have to do a lot of reading in the book, watching some of the videos that are in the ebook, and trying the best that you can on the homework problems. And then show up during class time. You're welcome to come at 10 like we are now. You can come at the 8:30 time with my other stat class and join with them, or you can catch me during online office hours. So I'm going to move all my office hours online, and I'll just turn on a meeting, and you guys can hook up during office hours and ask me questions, and I can work problems with you that way as well. Let me switch this over. What button do I want? This one. I'm going to try this. Who was that? Good morning, Noah. Share. Okay. So here's a couple of things. First, where is, this is what I want. I have to move you guys over there. Okay. All right, so you guys have my desktop coming through okay?
Yeah.
Okay, good. So this is us. So I will post on here if anything changes, but it looks like Zoom is going to work really well for us. So I'm going to try to use Zoom. We'll have this link for class, whether you come at 8:30 or 10. And this link is for office hours because I just put all my classes in the same office hours. And so use one of those two depending on what time it is, and come join the video chat. I'll also send you an announcement like normal. So if you don't have those set up, make sure you forward them to your whatever email you're currently using. And then we'll kind of keep a list of the calendar, right? We're going to do the best we can. I'll probably have to trim a little bit of the content out, but we're going to do the best we can to hit all of the course objectives to make sure that you guys are ready for, whatever class you're taking next. But this week, we're going to talk about section 5.4. And then next week, we're going to kind of ease into chapter 6 and see if we can't talk about confidence intervals in 6.1 and 6.2. I've had lots of questions about testing. Currently, my plan is to start out with some take-home style. Some of the tests I might put directly in my stat lab, so you'll take them in there. Some of them I might put in Canvas, so you can take them through Canvas. But we'll probably start out with me just emailing you a PDF that you either print out or fill out electronically and then submit back through Canvas. That's kind of our plan. We're going to have to just play it by ear and see how that all is going to go. I expect maybe to do a trial quiz maybe sometime next week if we can, or, and the chapter 6 test a little bit further down the road, maybe by the end of next week or the Tuesday after that. So don't worry too much about the testing. We'll get something figured out. But please try to make as much progress as you can on the homework. Questions about the calendar?
Nothing.
Nothing. Okay, good. Let me see what else I can do. I've got All right, so here's the notes. I don't have the chapter 6 ones quite done yet, but they should be done this weekend. And your quizzes that you took when I was gone at the conference should be done sometime this weekend and get posted for you too. And if I can get to a scanner, I'll scan them and send them back. Campus right now looks like it's going to be closed, even to me. They said I can't go back in my office. So we'll do what we can to try to get them back to you, as you know, somewhere down the road. And I will post chapter 6 in the regular place, and then we should be able to kind of go from there. All right, move this over and stop sharing that. Okay. One of the other things that's nice with Zoom is if you know, you can double click on one of these little guys and you should, whoops, that's not what I wanted. You should be able to pin like the dot cam, you know, so I'll let you kind of experiment with what view you're on and whether or not you choose to use, you know, the microphone or the video. I mean, it's kind of nice to see you if you have a camera, but it's not essential. But if you're just listening in from time to time, you know, type a little message in the chat, especially if you're having, you know, technical difficulties or problems or questions, and I'll kind of keep an eye on the chat so that I can answer your questions. All right, that's about it for the overview. How are we doing? Okay so far?
Good.
1, 2, 3, 4, 5, 6, 7 of you so far. So that's actually pretty good, right? If we could get, I'm kind of hoping, I don't know what will overload this. We're supposed to be able to have 100. I don't know what it'd be like with 100 people all on here at once, but I did a big meeting with the department the other day. I think we had 35 or so, and it seemed to work okay. So I think this might be a good platform for us. All right, so let's actually do some math and kind of help you get thinking about section 5.4 and sampling distributions. So sort of from here to the end of the book, we're going to be doing something called inferential statistics. We're going to make an inference or a guess about a population based on a sample. Okay, so let's say we were interested in coming on the news like Farsi does and giving an estimate for how long it's going to take an individual to recover from coronavirus. And so you want to be able to come on the news and say, it's going to take an average person 14 days to recover. Okay. And so how would you collect that information, right? If we had all of the data from the whole population, from all coronavirus cases of all time, we could just add them up and divide by how many there are and find the mean. But of course, we don't know, right? We only have a couple of people that we're currently classifying as being recovered. And since we know nothing about the population, we're going to have to make some estimates. It turns out that we're going to sort of practice doing this by looking at the average, right? By looking at the sample mean. It could be other statistics that we're trying to approximate as well. We could approximate the median, we could approximate the standard deviation, or other characteristics of the population. But for us, we're just going to explore this idea by considering what's the average of some particular variable that we're interested in. Okay, so that's kind of the setup. We've got a population. We don't know anything about it. And what we're going to do is try to estimate the parameters, okay, in that population. So we're going to try to estimate what's the average, in other words. So to do that, we're going to collect some data. Okay, we're going to take a sample. I haven't looked today. It's a little depressing. I try not to look too often. But it seemed like the last time I looked, there was one person that they had considered recovered from coronavirus, and it took about 2 weeks. So given that we only have information about one person, we could say, you know, if you want to know about how long it's going to take, it's probably going to take somewhere around 2 weeks based on this one case. Okay. but we don't have any idea if, how accurate that really is, right? It's better to estimate the population with one value than with nothing, but just because we have one case doesn't mean that, it's necessarily that accurate. It could end up being that one person recovered really fast and it's going to take most people 6 months. It could be that person was really slow and really people are recovering in about 3 days. We don't have any idea. But it would seem like the more people, the more data that we get, or the larger the sample that we have, the better the estimate's going to get. So once we have 2 people recovered, one takes 14 days, one takes 20 days, then the average would be what, 34 divided by 2, about 17 days. And now you'd say, well, it's going to take people about 17 days to recover based on this sample of size 2, right? Which should be a little bit more accurate than a sample of size 1. And as that sample size gets bigger and bigger, then our estimate for the average for the whole population should get more and more accurate. This is an idea that math types or stats types call the central limit theorem. It says that the larger the sample size, the smaller the standard error of the mean. In other words, the smaller the error is in our estimate for the population mean based on that sample. So if we're hoping to use information about a sample to estimate things about a population, then we should know a little something about the way about the sampling distribution, essentially. In other words, what does a collection of samples look like, and what can it tell us about the parameter that we're trying to estimate? And so that's why we're studying in section 5.4 sampling distributions. And then we're going to use them in chapter 6 to make what we call a confidence interval, which is going to be a statement about how confident or how accurately we think we're estimating these parameters. Are we good on the overview?
Yeah.
Yep.
Okay. All right. So, and I didn't hear from Alma or Noah. Are you guys listening in? Is it working for you?
Yeah.
Okay, I've
Can you
got
hear
you
me?
there. I thought Noah might be online. Let's see. Yep. Okay, good. He's just listening. Okay, perfect. So let me share my screen with you again. I think maybe sharing the screen would be the easiest. So I'm going to go to share screen. And I tried it kind of window by window, but I think the whole desktop seems to be the best. So you'll have to look at yourself, looking at me, looking at yourself over here on the side, right? Uh-oh, pinch out, bigger view. Yep. Oh, no, it hid that. That's interesting. Okay. So I'll make this a little bit bigger. All right, so here we are. You guys have these notes, and of course, these are just a section of the notes from the book. You can read the book, look at the videos, look at these notes, whatever works the best for you. And here's how it kind of goes. We're supposed to find a sampling distribution, think about this thing called the central limit theorem, and find a probability of sample mean. So that's kind of our objectives for this section, keeping in mind sort of the bigger picture, which was, right, that we're going to estimate things about the population based on a sample. So here's how it goes. Imagine that this population, in the case of coronavirus, is everybody, whole world, right? 4 billion people. And we would like to estimate the average time it's going to take to recover from coronavirus, currently based on a sample of size 1, right? So we'd say 14 days based on this one person. If we did samples of size 5, okay, then we could take a whole bunch of different samples of size 5. And then we could see what happens with all these different possible samples. I think probably the easiest way to do that is to just actually do a problem. Okay, so This particular one in here talks about some times to go to the grocery store. There are 4 numbers, right? And we're going to take samples of size 2. A couple of you have already asked me about a problem from the homework. And let me see if I can get to it. So I'm going to try one from the book. There's going to be that one that was right there in the notes that you can refer back to for a second kind of worked out example. But here's one from the book. Okay, let's see. I want this. I got to make that just a tiny bit bigger so you can see it. Okay, so here are some things that you guys are going to do. You are going to take a population. Oops. Okay, you can kind of read that. You can pull up the ebook in a different window if you want to look at your own copy of the book. This is just the book on page 270. You're going to take a population, find the mean and standard deviation, list all the samples, and find the mean and standard deviation of the sampling distribution. Okay, and essentially what we have is a very, very small population. We're going to talk about load-bearing capacities in thousands of pounds for 5 transmission line insulators. Okay, doesn't really matter what the data refers to. You could think about it as coronavirus cases. You could think about it as machine parts or melting points or lifetimes or whatever it happens to be in a different problem. But we're essentially going to have these 5 population values. And out of that, we're going to take samples of size, focus. We're going to take samples of size 2. Okay, now in real life, uh-oh, what just happened? Having some internet problems. That can't be good. You have internet problems, we're going to get shut down. We're going to do samples of size 2. And so we would never do this in real life, right? In real life, we got 4 billion people. Best case scenario, we would be taking samples of size 1,000. There are a lot of different samples or a lot of different groups of 1,000 that we could take out of 4 billion people. In fact, it would be 4 billion ways to choose the first, 4 billion ways to choose the second. It would be 4 billion to the 1,000th power, okay, which is a lot of samples. So we're going to sort of practice with a crazy, super small case that we can actually do with a pencil or maybe a spreadsheet. And then just think about it in the case of the larger sort of real life situation. All right, so let's, I'm gonna go ahead and do this in a spreadsheet because I think that's gonna be the easiest. So let me go to screen share. Let me pull up a window. I don't see it there, just a second. This away, pull this up, this away. I'll probably get a little better with this technology as we go. Okay, so I'm gonna share just a Google Sheets spreadsheet. So I just simply went to Sheets and said, open a new spreadsheet. This tool seems to be one that works pretty good. I'm kind of looking on my doc cam, it's kind of small. So let me make it a little bigger. Is that okay? Can you guys see that?
Yeah.
Yeah.
Yeah, okay. So if at any time, it looks like when I'm sharing, I don't get the chat window. And so I don't know how you guys can, maybe if I click this, what do I get? No, I still don't get the chat. All right, so for those of you, if there's technical problems when I'm sharing, I don't know what you do, just hang in there, I guess. The rest of you, if you know, I'm writing off of the camera or there's something you can't see, make sure you holler so that I, you know, adjust here. Not used to, you know, working this way. So if it's not coming through, make sure you point it out and I can try to fix it. If it's too small or if I'm off camera or something like that. All right, anyway, here we go. Here's what it said back in the book. And if you still got the doc cam up in a mini window, I've got these 5 values. I'm going to go ahead and put them in smallest to biggest order. So 19, 48, 56, 79, nope, 64, 64, and 79. Okay, so that is our entire population. If we were thinking about this in terms of coronavirus, we would have to take every coronavirus case that ever existed, right? This would be a big long list, right? If everybody in the whole planet got infected eventually, we would have recovery times for 4 billion people, and this list would be 4 billion numbers long, okay? So what we're interested in is trying to estimate the average of a population when we don't know what any of the values in the population. Okay, so what we want is to find the average. So I'm going to say, give me the average, right, of 1 through 5. And the average is going to be, for this data set, a 53.2. So the average insulator weight was 53.2 pounds. So we can actually calculate this because we know the data values. But if we're talking about recovery time, if we're talking about recovery time for coronavirus, we can't calculate this because we don't know the data values and we're trying to estimate this number. Okay, so that's the goal. And I think sometimes when stat students, first get to this section, it's really confusing because you're like, why are we doing all this work? You just calculated it right there. You already know it. Okay, and we only know it in this case so that we can do it as an example. So imagine that you don't know this number and we're trying to estimate it. Okay, that's the goal. The other thing that we can calculate is how accurate this number tends to be. In other words, we can calculate the standard deviation. And since this is the whole population, I'm calculating the population standard deviation, right, of these 5 numbers, and I end up with about 20. So we would say, based on these insulators, they weigh about 50 pounds plus or minus 20 pounds. Okay, in fact, 68% of all the insulators in this study would fall between, what is that, minus 20 is 33 and 73 pounds. Okay, but we don't know this number and we want to estimate it. So here's how you do it. You take all the possible samples and you look at all of their means. Okay, so the first thing you could imagine is, what if I do a sample of size 1? Okay, how many different samples would we have?
1.
We just do 1 sample, yeah, 1 at a time, but how many different possible samples could we do if they were of size 1? Like we could pick
5.
1 person. You could pick the 19, right? Or if you pick 1 person, you could have picked the 48. So it turns out there's 5 different ones, right? You could just pick each of these numbers individually. If you happen to just get lucky and pick the 56, then the 56 would be actually a pretty good estimate for the 53. But if you were a little bit unlucky and picked the 79 or the 19, then the 79 and 19 would be a worse estimate for this 53. Does that make sense? Okay. But if you know nothing about this 53 at all, picking at least one of these people gives you at least an idea of what this value might be. Okay. That's like our coronavirus case where 1 person has recovered in 14 days. I don't know what it really tells us about the whole population, but it tells us a little bit of something, right? Just not very much. So what we're going to do is try samples of size 2. So if I pick 2 of these people and I took the average, then I'm going to claim that that average is a better estimate of the 53 than it would have been had I just picked 1 of these people. Okay, so we want to make all the ways I can pick 2 people. So give me a way I could pick 2 people. I could pick what and what?
19 and 48.
Sure, 19 and 48. I could pick 48 and 56. I could pick 56 and 79. Okay, and we're going to do this with replacement. Okay, and there's some technical reasons for that, which are not really that important, but you could also pick 19 and 19. Okay, so there are 5 ways I can pick the first number, and then there's 5 ways I can pick the second number. So there's 5 times 5 or 25 samples. Okay, so I'm gonna just list them all. Check this out, here we go, I'm gonna list them. All right, so we could pick 19, and then we could pick 19. Might run out of room, I'm gonna pick it right here. 19 and 19. Okay, I could pick 19 and 48. Okay, I could pick 19 and 56. I could pick 19 and 64. I could pick 19 and 79. Are you with me?
I've got a question.
Sure.
Yeah, that's something I didn't understand on the homework. Why, if there's only one 19 value, why are you able to pick it twice?
That's a very good question. It would be like dealing a hand of cards and then shuffling the deck and then dealing again. Okay, like picking a card from the deck and then putting the card back in and picking again. So we're either going to do with replacement or without. The problem without replacement, in other words, if you deal 2 cards, you guys know that it's 52 on the first, but only 51 on the second. The problem with that is that we have conditional probability, and the probability changes just slightly. It turns out that in practice, it doesn't really matter, because if we were picking a person, say, from the United States, there would be 350 million people to choose from. And whether I put that person back in or not back in, what's the chance I would pick up that same person on the second pick, right, out of 350 million? It's like so little, it's negligible. So because of the way the mathematics works, and I guess for our class, we're just kind of getting our head wrapped around the concepts, and why this is the right formula is just going to have to come later in a second semester stats class where you like prove the formulas are what we said they were. It just works out if we do it with replacement because of the conditional probabilities. Okay, so you pick one of these numbers, you put it back in, shuffle it all up again, pick one of these numbers. So 1919 becomes a possibility. Check this out. Now I could pick what? 48 first, right? But I could pick any of these numbers second. And since I'm on the computer, I can just copy and paste them in. In fact, I can grab this and pull down, right, and fill in all the 48s. So it's kind of way faster to list them with the spreadsheet than it would be to list them by hand. And so then what do I want? I want all these over here, and I want a 56 first, right? And then I'd say, okay, make all these 56. And then I want all these, right? And I want a 64 first, okay? And then I want all these, and I want a 79 first. So there's some really nice advantages for using the spreadsheet because you can copy and paste. It's a lot faster. It obviously does the calculations for you, but technically you could do this by hand, okay? Nobody does. And in reality, nobody does this at all because of course, we're talking about this list is 4 billion long, and this sample isn't just 2 people, but maybe it's a sample of size 1,000. Okay, so it's just ginormous. And that's so big that probably a computer can't even do it without it being, a special large number, floating point, whatever it happens to be. All right, so now we want to know what the average is. If I happen to pick these 2 people, then of course I would add them up, divide by 2, just like normal, 38 divided by 2, 19. All right, or I can let the computer do it for me. Average these 2 numbers. And of course I get 19, just like we said. So 19 and 48, add them up, divide by 2. What do I get? I don't know, I get all these. I can just drag it down and do all the averages. So I get 33.5 and the rest of them. So if I picked the 4864, so let's say I picked, for my sample, I picked 48 and 64, then I would get an average of 56, and 56 would be a pretty good estimate for this 53. Okay, if I happen to pick the two 19s, then 19 is not a really good estimate for the 53. But notice that when I look at this list, you know, 52 is a pretty good estimate for 53, 48 is not bad, 63 is pretty close to 53. And what I'm arguing is that all these values are going to be the possible estimates for this mean. So what I want to do is I want to look at this distribution. This becomes my data set, and I want to look at, see what this distribution looks like. Because remember, I don't know the 53. So what I'm going to do is I'm going to take a look at a histogram. So I want to build a histogram. So I say insert a chart, and it makes this giant chart because I'm in this big mode. So I'll squish it down a little bit. I'm going to turn it into a histogram. Okay, and you can clean it up a little bit if you want to, but this is a histogram, right, of the means that we just calculated. And now based on this, what does it look like the average is?
Average.
Yeah, so where's the average? Like, say that one more time.
54.
Yeah, like 54 looks like about the average, doesn't it? Some down here, some up here. 54 looks like about the average. And what are we at? What was our actual value? 53.2. So if we take the average, it's a pretty good estimate for this 53.2. So let's go ahead and do that, right? I'm gonna close this, make this a little smaller so it's not in the way. Make that a little smaller over here. And then let's just find the average of all these numbers. So you'd say equals the average, okay, of this whole list. And check out what it is. 53.2. And so if I average all the sample means, I get the actual population average. In other words, it's like perfect. It's a perfect estimate.
Yeah.
Now let's see how well, how much we could miss by. To do that, you find the standard deviation. And again, since this is all the values, you use the population standard deviation of all these values. And it came out a 14.9. What this is saying is that based on a sample of size 1, we would expect people, or these were weights of insulators, we would expect the insulators to range to be centered around 53 plus or minus about 20. But if we did samples of size 2, then we would expect the estimate to be a 53, but only have an error of plus or minus 14. In other words, because we picked samples of size 2, the error in our estimate is smaller than it would have been with samples of size 1. Okay, so that's what this is telling you. In fact, this has a name. Statisticians call this the standard error of the mean. So this is how much is this estimate likely to miss by, right? And it would be about 14 on either side. So that would be like you go on the news and, you know, Trump or Farsi or one of the Surgeon General comes on and he says, you know what, we expect coronavirus to people to recover in 14 days plus or minus 4 days. And then you'd say, well, that's nice, but that's based on a sample of how many people? And you'd say, well, based on the 2 people that we've had so far. Okay, so this number's still pretty high. If we did samples of size 3, then we would expect a better estimate, and we would expect this number to come down. Okay, If we did samples of size 4, that's almost the whole population. There was only 5. And so we would expect this number to come down further. In fact, if we did a sample of size 5, if we picked all these people, then we would get exactly the mean and there'd be no error at all because our sample was everybody. Okay, so that's really the big idea. It says, I don't know this number over here. I don't know what the average is. I'm going to estimate the average based on a sample. And the standard deviation of my distribution of sample means is going to tell me how accurate that estimate is. And then that estimate should get better and better as the number of people in my sample goes up. All right, so that's the big idea. How are we doing? Did it make any sense?
Yeah.
Yeah.
Okay. In the book or in math types, they're going to call this whole idea of the estimate getting better and better, they're going to call that the central limit theorem. It says that in the limit, as I get more and more and more people in my sample, this gets more and more and more in the center. In other words, the estimate gets better and better. And there's a bunch of technical difficulties, of course, some mathematical proof about proving that that's actually true and that it happens. And there are some considerations, that are required, or some hypotheses that are required before that can happen. If we, what do you guys got? You still got that screen. Okay, so I'm going to jump back for a minute. Let me see. Stop sharing this. Start sharing this. Okay, so they went through it here with 4 numbers, samples of size 2. And here's their samples. Here's their histogram. And then here's the way their spread turned out. What we notice is that they come up with, based on, where is it? Sorry about scrolling all over, trying not to make anybody seasick. Central limit theorem says that no matter what the population is, my spread, my error on my estimate is going to get smaller and smaller. Okay? And the formula that you come up with is right here. And of course, in true Larson fashion, he gives you the formula before he explains it, right? And I think it probably, I like to just kind of think about it first and then get to the formula. The question is, why is this the right formula? Okay. And the best I can answer is because it works, at least for now. There's a mathematical proof that yes, that's the right formula. But I think it's beyond the scope, of what we're doing. So you just have to take it on faith for now. Or if you don't want to take it on faith, you can just go Google it and read more about it. But I'm going to try it. So here's our spread. According to the formula in the book, this number should be equal to the standard deviation of the population, which was in A8, divided by the square root of the sample size, and ours was size 2. Okay, so bam, same. This is the standard deviation done the long way, difference from the mean squared, divided by how many there are square rooted. This is the formula we used way back in chapter 2. Okay, this new formula that I just typed in was the shortcut formula. And you could either do it the long way, take the shortcut formula on faith, which is what I would probably do, or keep taking some stat classes and we'll prove that shortcut formula really is the right formula. But notice that it is giving us the right value. So I'm going to take the shortcut formula sort of on faith. Okay. And so how do I get back? It doesn't switch windows very well. And when I share the desktop, it's too small. So I'm just going to keep flipping back and forth. Okay, so the mean of the sampling distribution is the mean, and the error is the standard deviation divided by the square root of the sample size. Shortcut formula, right? Or you can use the old formula and go the long way. Okay, so what does all this mean? Right? Maybe we should do a problem. So let's get down here. You can read a little bit about this stuff. Let's get down here and take a look at what this means. All right, so here's a nice problem. And I think you guys can see it. I get kind of two phones going at the same time to try to see what you guys are seeing. It says the graph at right shows the length of time people spend driving each day. Okay, so here's some different driving distances. Randomly select 50 drivers age 15 to 19. So we're going to be interested in this data right here, right? What's the probability the mean time they spend driving is between 24.7 and 25.5 minutes? Okay, so according to this, it says that the average is 20.7. All right, so working over here, let's see, I want to unpin that so you can see it. How do I, this is the easiest way. Maybe I'll just unpin that. And then you guys can probably make the dot cam the biggest. And then I'll just go back. It's in the book too. If you want to pull it up in the book, you can look at the actual problem. Okay, so maybe I should do that. If I can find what page it's on. Okay, this is 5.4. And it's right here. Here's the miles to go in the car. Oops, too zoomed. So if you're pulling it up in the ebook in a different window, it's page 266 in the book. And so there's the problem. And here we're gonna work it out. This is page 266. And now that's got to be bigger for you to read it. Maybe about there, I think. And I'm gonna pin mine on the screen. Oh, maybe I am. How do I pin it? Pin it. There we go. Okay, there we go. That way I can see it. All right, so I got you chat people back on the line there. So if you're hollering, I'll try to pay attention. Okay, so here's what it says. The average person in the 15 to 19-year-old range drives 20.7 miles. So the average is 20.7 miles. The standard deviation was 6.5 miles, and driving distances are normally distributed. Okay, so basically it says, if this is our histogram, or if this is a smooth curve that estimates our histogram, come on, focus. No, it doesn't seem to want to focus too well. Then half of the people are less than 20, half of the people are more than 20.7. And since the standard deviation, right, the standard deviation is this distance right here, is 6.5, that we would be up to, what's that, 27.2 and down to, I don't know, give me a 20.7 minus 6.5. I get 14.2. Okay, so how many people would we expect to fall between 14.2 and 27.2? You guys remember? It's in the beginning of chapter 5.
68.
68%. Okay. So if you picked one driver, right, at random, and that driver was had driven 23 miles this week, would you think that was weird, or is that pretty normal?
Pretty normal.
That seems pretty normal to me. What if that person had driven 50 miles that week? Then you'd say, well, that's pretty extreme, wouldn't you think? Okay, so let me do a couple more. 2 standard deviations goes from here to here. So 2 is 6.5 more. What's that? 33.7. And down, subtract another 6.5. Is that 8 something? 14.2 minus another 6.5, 7.7. Okay. So how many people would you expect to fall in this range? And you'd say what?
97.
95, it turns out. Little more, but about 95. So it would be weird, right? In fact, only 2.5% of the people are up here. So it'd be weird if you picked a driver at random and they had driven more than 34 miles. That'd be pretty rare. In fact, we could go one more standard deviation, 3 standard deviations, right? That's over about here. 3 is another 6.5, 39, 40.2. And down another 6.5 is what, 1.2? So 99, right, point a little bit, percent of all of the drivers are going to be in this range, between 1 mile and 40 miles. Okay, we good so far?
Yep.
Good. Now, here's the deal. What if I erase this number? Like, I don't know what the average is, and I'm going to have to estimate it. I mean, clearly you're not going to estimate it if you know it, but if you don't know it and you're asking yourself, I wonder how far, 15 to 20-year-olds drive every week, then we might take a sample of some 15 to 20-year-olds. And in the book it says we took a sample of 50 drivers. Okay, so we took a sample of 50 drivers and we said, I want to estimate the average of 20.7 using the average from my sample of 50 drivers. Okay, so you find out the average of those 50, and let's see, what does it say? You'd find out that the average of your sample of size 50 is centered right at the same place, 20.7, because the average of all the samples is equal to the overall average, which in this case was the 20.7. Okay, but this is the average of all the samples. So if you took one sample of size 50, it's likely to be a little higher. Another sample of size 50 is a little bit lower. If you happen to just get really unlucky and you pick 50 people and they happen to be the 50 people that drove the most, then you probably have a pretty bad estimate. Okay, but in general, these samples that you took are going to be distributed somewhere around this 20.7. In fact, they're going to have a spread, okay, that's equal to sigma divided by the square root of n. So since sigma in this case was 6.5, we're going to divide by the square root of 50, because there are 50 people in our sample. Going to need a calculator for that. I've got 6.5 divided by square root 50. I got an error. I haven't used this calculator too much. Try again. 6.5 divided by square root 50 looks to me like about 0.92. Okay, so maybe I'll just call that 0.9. So 20.7 plus 0.9 is what? 21.6. And 20.7 minus 0.9 is 19.8. So what we're saying is, this was 0.92, right? Sigma. Okay, it was 0.92. Try to keep that on the screen for you. So what we're saying is, of all these samples, right, the samples, 68% of the sample means should fall between 19.8 and 21.6. If we take drivers one person at a time, we would expect them to range from 14.2 to 27.2. But if we take samples of size 50, we would expect the average to range from 19.8 up to 21.6. sorry about that. Okay, you guys still there? Still with me?
Yeah.
All right, so what we're saying is that if I take a sample of size 50, I make a much better estimate for the 20.7 than I would if I had samples of size 1. Okay? So let's say I took a sample of size 50 and my average was, here, let's do a couple more first. 2 standard deviations is 0.9 more, so that's 22.5. And I take away 0.9 more, 18.9. And then I take one more, add 0.9 more, it's 23.4. And I subtract 0.9 more, I'm down to 18.0. Okay, so 99% of these samples should fall in this range. These are samples of size 50 again. So if my sample of size 50 showed that, that an average person had driven 24 miles, would that be kind of rare?
Yeah.
And the answer is yeah, right? There's only like 0.5% over here and 0.5% on this side. So, so your accuracy of your estimate gets better when the sample size gets bigger. Okay, and that's pretty much what we're saying. So the question asks this. It said, what's the probability that the mean distance traveled is between 19.4 and 22.5? Okay, so 19.4 and 22.5, I wish they would have done 19.8. Maybe I subtracted wrong, I don't know. 19.4 is about right there, and 22.5 is about there. So what they're asking is, what's the chance that you're in this range? Right, that's what they're asking. Okay. And so that's an area under the curve type problem. But I mean, you can sort of estimate it, can't you? 68% are in this range, right? 99% are in this range. So what do we got here? It looks like about, that's about 70, 85% or so would be in this shaded area. So there's like an 85% chance. And of course, if you want to find that area exactly, then you're going to want to use a calculator. Might want to use Desmos like we did the week before spring break. And let me throw the book under there. I'll show you how the book did it. The book did it 2 different ways. The book. Hey, Tack. Hang on a second. I'm having some internet problems. Let me see if I can fix it. I need some more bandwidth. I need more bandwidth.
Well, I just streamed the video in there. So
Somebody's streaming video because I can't be online. Okay, I think I might have that fixed. We were watching videos in the other room and it was killing my internet bandwidth.
What's up?
Oops, come on, focus. Boy, it sure won't focus on that, does it? There it goes. Okay, you guys all still there?
Yeah.
Okay, sorry about the interruption there. It says, okay, find this area, right? This blue area between 19.4 and 22.5. Okay, and it's going to use the book to do it. I would probably use Desmos to do it like we did before. You can look at how they did it in the book by just looking at the book. Okay, they used a TI-84 to do it, and it gives the directions on how to do that right over here on this page. But let me just pop back into Desmos because that's how we did it before spring break. And I think that might be the easiest. I think for me, it's the easiest to do because I got the computer already on. It's right in front of me here. So I'm going to share. Let's see. I'm going to go to a window with Desmos. And I'm going to share it with you guys. Where is it? Hey, what happened to it? It's not there. Hang on. Oh, there it is. I think that's it. Okay, good. And I don't know how to make it bigger. It's like the zoom isn't quite right. Can you guys see it okay?
Yeah.
Yeah.
Yeah, okay.
Yeah.
All right, so what do we got? We've got that normal curve, right? So what do we put? We put, if you can't remember what to put, because maybe it's been a week or two, go under distributions, right? And it'll type a normal distribution for you. And then it kind of prompts you for the other information. So you're going to say, I want the mean. The mean was 20, what was it? It was 20.7, right? And the standard deviation was the standard deviation of the population divided by the square root of the sample size. So we did 6.5 divided by the square root of 50, right? And of course, you could just put that number in there. We calculated it, it was 0.92, okay? And so where is this thing, right? Well, it's centered way over here at 20.7. And so there's our curve right there. And if you want it all prettied up, you can, change the values on the axes so that it, fits a little bit better. Something, oops, that's too big. 0.8 maybe, 0.5 maybe, maybe the 1 there. All right, that looks pretty good. So there it is. So there's the picture from the book, right? I just made it in Desmos. If you want to find the area under the curve, you're going to say, that's all of it. I want the area from what was in the problem. The problem said between 19.4, right, and 22.5. So we get 89.6%, or about 96%. And essentially what that's saying is we're pretty confident, right, that this is a good estimate for the average driving time for those 15 to 20-year-olds. Because if we do this process, an average of 20, we would be right, in the range of 19 to 22 would happen 90% of the time. Now, if you got an average that was, way out here somewhere, like 25 miles in a week, then that would be exceedingly rare, okay? And that would tell you you either picked a really bad sample, or maybe those kids are driving more than you think they're driving, okay? So you don't have to use the Desmos tool to find this. I kind of like Desmos because it gives this nice picture. You can certainly use a table in the back of the book or your TI-84. To be perfectly honest with you guys, this is not what I would focus on in terms of skills. This is a nice skill to be able to actually get this number accurately. That's cool. But I think that the more important thing would be that you could estimate. And the best estimates are how much falls within one standard deviation, 68%, 2 standard deviations is 95%, 3 is 99%. So if you knew that, you could just look at this area and say, well, that looks like about 80 to 90% of the areas in here. And even if you can't get the number exactly, getting this, knowing that you're supposed to be getting this area and being able to estimate it, that's the most important thing. And then you can pick your favorite tool for actually getting this, to be the right number. And you're going to know it's right or not because you're going to push return and you're going to get, a green check mark. And if you don't, then go back and play with the numbers a little bit more. Okay. And if you've done that 2 or 3 times and you just can't figure out what's going on, then log in during the office hour time and I'll work through it with you and we'll try to figure out what's happening.
I have never thought of my work.
Okay. Stop sharing. Come back to me. All right. So that is the sort of the long and the short of this this section 5.4. It's going to get us started on trying to estimate population parameters, in this case, the average of the population. We want to estimate it based on a sample. And the big idea is that the bigger the sample, the better the estimate. Okay, so I've been blabbing for a really long time. Do you guys have any questions? Anything just jumping out right away that's bothering you?
Nope.
Nope.
Okay. I'm going to let you guys go then and give it a try. You know, be patient. I know it's going to be more of a struggle, you know, trying to connect online and not being able to, you know, I mean, it's harder to ask questions live in this format. But I will be here this afternoon in office hours. So like at 11:30, I'll get back on in the office hours. And if you want to drop back in, you can. And then I will be here Monday, Wednesday, Fridays at 10, and then back at the regular class times. So try some problems in my math lab. I think that at this point, you know, I wouldn't worry. Well, I would worry, I suppose. I don't know. Don't get too stressed out about the grades. Okay, I think that that we will figure something out that seems fair. You know, we'll have to do a little bit of testing. I know that there's been a lot of discussion around the office about proctoring. There's some concern about the whole class being sort of a take-home. I'm not really too worried about that. I'm kind of more worried about giving you opportunities to share what you know. When we get all the way, you know, like I said, we'll probably start with some take-home things that you'll submit through Canvas. We might do some tests that are either probably right in my stat lab, so that they'd feel like doing another assignment, except that it would be like, you know, one try instead of infinite tries. And by the time we get to the final exam, I don't know, maybe the school will have a better solution for us. But it doesn't look like we're going to be back in the classroom at this point. It looks like we're kind of struggling on our own, working independently, and you know, trying to communicate online, at least for the rest of the semester. But the goal is for us to learn as much as possible to get you guys credit for the class, and, you know, have you move on down the road and have this be the smallest impact that it can be to your, you know, to your pathway and to your program. Okay. Anything else I can tell you today before we log off?
Professor Brad,
Yeah.
do we have a test coming up that I should know about online?
No, not yet. And I will post anything in Canvas and send you an announcement.
Okay.
I will probably do some really small quizzes just to try out some different modes of testing. So I might do like a little 5-question quiz in Canvas, or a little 5-question quiz in my stat lab, so that we can just try it and see how it's going to work before we get to a bigger test.
Okay.
Okay. The next thing that I would expect is I will probably send you a PDF, right? Just a take-home kind of paper test that you can print out or fill out electronically and submit back through Canvas. That's what we'll probably do first. Okay. Okay. Well, if you don't have any more questions for me, I'm going to let you go. And please check back in. Remember that you can always email too if it's at a time when I'm not online. And I'd be happy to support you as best I can.
Thank you.
Okay. Good to talk to you all this morning. Have a great weekend.
Bye.
Mm. Mm.